Okay, so dear colleagues, let us start with our first BIMS integrable system seminar this year. And today I'm happy to introduce Didina Serban, our speaker in person here. And we'll talk about fermionic point of the q-deformed Haldane Shastry model.
Okay, thank you, Ivan, and thanks to the organizers of the seminar for giving me the opportunity to give a talk here. So I will talk about some relatively recent work, a series of work on the formation of long-range spin chains from the Haldane-Shastry family, and in particular, I will concentrate in part of my talk to the free fermionic point of this spin model. So this is part of this work originates in a common work with Jules Lammers and Vincent Pasquier from 2020, and then two more recent works with Jules Lammers and our common student Adel Ben Moussa, a PhD student, and one of our master students, Ayman Toufik. So, oops. I will talk about long-range integrable models, and I'm particularly interested in aspects of the quantum aspects of the these integrable models. My motivation is coming from different types of deformations that arrive in ADS-CFT integrability. Also, there are relationships with two-dimensional conformal field theory, TT-bar deformations. So we have deformations of Heisenberg-like models, Heisenberg-like spin chains. And I'm interested in the properties of these models. So the best understood and studied integrable models, spin chains, are those with nearest neighbor interactions, and they are solved by algebraic Bethe-Ansatz. But this long-range deformations, they are less understood because this algebraic structure is which functions for the nearest neighbor models is not working when longer range interaction is switched on. In particular, what are called wrapping corrections are not well understood. But there is a particular class of models that for which mathematical techniques were developed during the years, which allow them to be solved to a large extent. So these models are trigonometric interactions. So I will explain what does it mean a little bit later. So these models that I present here, they have some common characteristics, like they are not solved by Bethe-Ansatz because the scattering phase is very simple, so there is no Bethe-Ansatz. There are no bound states like we have in the case of Heisenberg spin chains, and they possess extended symmetry beyond the SU2 or SUN symmetry. And in some cases, well, in the rational case, these are, or in the isotropic case, this symmetry is the Yangian symmetry, or in the q-deformed case, the extended symmetry is quantum affine symmetry. So the rough plan of the talk will be to introduce first the isotropic XXZ-like models, and I will describe the Haldane-Shastry model and how it can be solved via generalization, which is the spin Calogero-Sutherland model. And then I will introduce the anisotropic XXZ-like long-range version of a long-range version of XXZ model, which I would like to call Uglov-Lammers model, because the persons who most contribute to understand this model are Denis Uglov and Jules Lammers. So this will be alternatively, I will call this the Q Haldane Shastry model. So this is more or less what we did with Vincent and Jules in 2000, adapting the algebraic structure that functions in the case of the spin Calogero, Sutherland, and Haldane Shastry to the q-deformed case. And then I will explain how to take the root of unity q equals I limit, which are the characteristics, simplifications of this, and also pathologies of this limit. So this will be a kind of long-range version of the XX nearest neighbor model, which is known to be solvable by Jordan-Wigner transformation in terms of free fermions. So in this long-range setting, also the model will be solved in terms of fermions, but they are naturally non-unitary, and the existence of this fermionic transform is also related to the reformulation of the model as a GL11 spin chain. And in this case, the odd length and even length cases are very, very different. So we have an analysis of the odd length case in a PRL from 2024. And we have announced some results for the even length case later that year, but the even length case is a little bit less studied and understood. Okay, so let me introduce, well, there are some specialists in this room that know probably better than me this model, but it's generally not so well known. So it's a model where n SU2 spin in the spin 1/2 representation are situated on a circle with periodic boundary conditions. They are situated on a regular lattice, which is given by the nth root of unity on the circle. And the Hamiltonian is defined in terms of spin permutations, spin exchange, which can be written in terms of Pauli matrices in this simple way. So Pij is a permutation of two spins at positions I and j. And the interaction between, the strength of the interaction between these two spins is given by some potential which decays as the one over the chord distance square or sine square. So this is why the model is called trigonometric, because the potential of interaction between the particles is given by a trigonometric function of the separation. So this model was proposed independently by Haldane and Shastry in 1988. So it's, of course, it's a long-range version of the Heisenberg spin chain, which would be just sum of the permutation of nearby spins. So it looks more complicated than Heisenberg, but in fact, the spectrum, the properties of this model are much simpler than the ones of short-range XXX model. And the excitations are described by idealized magnons and spinons that which do not have other interaction except for some statistical interaction. So this model can be considered as a model of a statistical interaction or exchange statistics in exclusion statistics in one dimension. This is also why there is a relationship between this model and two-dimensional CFT realization. So this was understood in the beginning of the 90s by a group including Haldane and my PhD advisors, Denis Bernard and Vincent Pasquier. So the algebraic structure was understood in this paper here that will be one of my main reference papers in the talk, because yeah, a lot of the algebraic structure is defined there. So one of the important properties of this model is that it has Yangian symmetry, which means that the spectrum has a very large degeneracy. So the degeneracy is given by this extended symmetry, Yangian symmetry, that will appear a little bit later in the talk. So there is of course, the low energy description of the Heisenberg model around the antiferromagnetic state is given by conformal field theory with symmetry SU2. So the Kac-Moody algebra SU2 at level k equals 1. So there is a nice relationship between the Yangian symmetry, the Kac-Moody symmetry, and also the spin-on description of the CFT, which was given in the beginning of the 90s as well. So I am reminding these properties because this is also what we would like to achieve for the new model that I am going to present to you today. So let me explain a little bit better how the spectrum of this Hamiltonian can be characterized. So it's given, the spectrum is given in terms of a collection of integers that were called motifs in this paper here. So these motifs are a collection of M being the number of magnons, if you want, quasi-excitations of the magnetic system. They take values between 0 and n, a little bit like the momenta for the magnons in the short-range Heisenberg model, and they have the property that different numbers, different quantum numbers, differ by at least 2 units. So you can imagine a system of free fermions where you have the momenta which are labeled by integers between 0 and n, and then in each orbital you can have at most one excitation. So that will be a fermionic description of a fermionic system. Free fermionic system, you will have the energy is proportional to p to momentum square. And here there is this repulsion, statistical repulsion that is given by this relation, which tells you that you cannot occupy two successive orbitals by these numbers because the mu's do not like to sit, the magnons do not like to sit close to each other. So apart from this restriction, the energy is given by one particle as a sum of one particle magnon energies with a dispersion relation which is well up to some linear term. It's a parabolic dispersion relation. So you see that if you occupy, if you have particles with fermionic statistics occupying or not occupying each of the orbitals will give you a number of states which is to the dimension of the Hilbert space, 2 to the power n. But here, because of this restriction, you see that you have much less motifs than a number of dimension of the Hilbert space. So you have to have the degeneracy, and this degeneracy is related to the existence of the Yangian symmetry. And each Yangian representation will be characterized by one of these motifs. Now, if you want to see to see the comparison with what happens in the nearest neighbor XXX model, we have a model which interpolates between Heisenberg and Haldane Shastry, and it has the potential that I was considering earlier. Instead of being 1 over sine square, is in fact a Weierstrass function. And this Weierstrass function has a parameter which is related to the period. So when this parameter is varied between 0 and infinity, you can explore, interpolate between Heisenberg and Haldane Shastry. So you can see what happens with the bound states in the spectrum of the XXX model. And you see that the bound states, when you go to the Haldane Shastry limits, they go into the descendants of Haldane Shastry. So you will see bound states disappearing and degeneracy is occurring. Yes. M can take any number from 0 to n over 2, because you can put, if you have this exclusion rule, you cannot put more than n over 2. Yeah. M is any. So the motif is also characterized by the number, in the yeah. So you can have any number of mu's from 0 to m. Sorry, to n over 2, or the integer part of n over 2. Okay, so now this the solution of this model was obtained by this group going through the spin Calogero, finding the solution of the spin Calogero-Sutherland model. So what is the spin Calogero-Sutherland model? I have two different versions here, which I will label by bosonic and fermionic. So I have again this permutation of spins here, which so now my particles have spin, but also can move freely on the circle. So there is a kinetic term associated with the movement on the circle. And the interaction between the particles will be given by this 1 over sine square term, essentially. But now we have also a coupling constant for this interaction term, and beta is a free parameter that we can control. So when beta goes to infinity, intuitively we see that this potential will become large, and the particle will like to sit in the minima of the potential of the part which is strongest when beta goes to infinity. So the particles will like to fix in the on their positions, equidistant positions that are given by the roots of unity. So this trick was proposed by Polychronokas. It's mathematically it's very subtle, so people here reinvestigated this limit. So it's a very interesting limit. So that's how the once one gets a solution of this model, one can take the limit of when beta goes to infinity to get a model which will be just exchange of spins times this potential. This part here will become just the potential of the Haldane-Shastry Hamiltonian, and then the rest will be just a constant term plus this kinetic term, which will become subdominant if one rescales properly the Hamiltonian. So the spin-Calogero model is solved using the degenerate double affine Hecke algebra, which is algebra which is spanned by the collection of the positions of the particles and then some operators. Each of this group of variables mutually commute. So these operators here are kind of generalized momenta, because they are generalizing this the momentum of the particles. But they now include a part which contains permutations of the positions. So these operators Kij will permute the positions of the particles on the circle, and they have some particular expression which ensures that the operators commute. So these operators are called Dunkel operators. So the Hamiltonian can be diagonalized now once we want to diagonalize this Hamiltonian on functions which are completely symmetric or antisymmetric by permutations, by simultaneous permutation of spin and coordinates. So we take out a part which is factor of which contains the fractional statistics. If you want, it looks like a Laughlin wave function, and then the part the leftover is a part which is polynomial in the coordinates of the particles, and also contains spin coordinates, and on this space of functions, if you permute simultaneously spins and coordinates, then you'll get either the same function or the same function with the opposite sign. So the bosonic or fermionic nature is related to these two signs. So more explicitly, if you want to write a particular function in this space, so you are taking the spin the spin space, all spin ups, and then you flip some of the spins at the particular positions, and then you multiply this spin function by a function of coordinates, and symmetrize or anti-symmetrize, and you see that because this spin state is symmetric by permutation by spins. If you want to have a symmetric or anti-symmetric function, you will have to partially symmetrize the two groups of coordinates depending on the position, which spins you have flipped here. So on this space of functions, one can define a projection. So this is the space of function that I have defined here more abstractly. So on this space of functions, I can, once I act with one of the permutation at the right, then I can transform it into the other permutation with a plus or minus sign. So I will define this action of the projection of which will transform my permutation of coordinates into a permutation of spins. So you see that now if I take the sum of squares of Dunkel operators, they will depend on permutations of the coordinates. I apply the projection. I transform the permutation of coordinates into permutation of spins. So now I will get some Hamiltonian which contains only permutations of spin here, and this is the Hamiltonian that I will get after the projection. So it's a bit complicated procedure, but this ensures that I can analyze. In fact, I can diagonalize the Dunkel operators. I can start by diagonalizing the Dunkel operators here, and then I transfer through the projection all their properties to the full wave function. Moreover, once I have this object defined, I can also define monodromy matrix, mimicking the construction of the monodromy matrix of the Heisenberg model. So I take the product of Lax matrices on each of the sides, and then I'm using the Dunkel operators as kind of inhomogeneities. And then after constructing this abstract monodromy matrix, I take the projection to the space of, I will change all the permutation in spins into the permutations of permutation of coordinates into permutations of spins. In the rest of the presentation, I will work with the fermionic space because it's more useful. So I can now analyze my the monodromy matrix more or less as I would do for the XXZ spin chain. But one important difference is that integrals of motions that I mentioned previously. So for example, the Hamiltonian, it belongs to a series of operators that are generated by the quantum determinant of this monodromy matrix. So it's given by the conserved quantities are given by the projections of the powers of kth powers of the Dunkel operators. So in this formulation, it's immediately obvious that the quantum determinant. So since the quantum determinant commutes with all the elements of the monodromy matrix, then the conserved quantities are given by this. Then the Hamiltonian commute with all the elements of the monodromy matrix. So therefore, we have our generators of the Yangian symmetry, and we can also proceed to build the. I mean, one of the problems of this of the realization that the Hamiltonian commute with the elements of the monodromy matrix is that we cannot use Bethe-ansatz because the B operator, which would be used to build the Bethe-ansatz functions, will commute with the Hamiltonian, so we cannot use them to build our space of state. So we have to do something else to diagonalize, to construct our wave functions, and this is done by diagonalizing the Dunkel operators. So the eigenvalues and eigenfunctions of Dunkel operators are known from the theory of McDonald-Dvorak non-symmetric polynomials. So the eigenvalues are given by well, this fixed part here, which depends on the coupling constant, and then on some integers, which are ordered. So in the freezing limit, so when we send beta to infinity, the positions will become the roots of unity. Also, the objects that are relevant, the eigenvalues become equal to these numbers rescaled by beta, and then this fixed quantity here. So we see that when beta goes to infinity, the information that comes from the numbers k is lost, except the fact that whenever we have a pair of repeated k, we know that we have to have a reversed spin because of the condition of antisymmetry here. So we know that if the two numbers k will be, so if this part if the powers of z will be equal, so we cannot antisymmetrize on the coordinate part, so we'll have to antisymmetrize on the spin part, so we'll have to flip a spin. So we know that whenever we have a repeated power of k, we have a reversed spin. So this will be encoded. This information will be encoded in the numbers that I call the motifs, and they come with. So they also can be written in terms of some partition lambda, and in the end, the wave functions for the Yangian highest weight states are obtained in terms of Calogero system with beta is equal to 2, where these polynomials here are Jack polynomials corresponding to the partition lambda. So this is how this motif description here appears. So if you are trying to do this on directly from the to take the non-symmetric McDonald and Jack polynomials and do the freezing limit, this is not clear how it happens. There are some partial results for McDonald polynomials when one of the parameters of McDonald's goes to 1, which would be equivalent to this limit beta goes to 0. So there are some results by Alexanderson and the collaborator. And we also looked a little bit at this problem. But yes, that's something that has to be clarified. Okay, so that's the part that I wanted to show for the isotropic model. Now, this story goes almost identically for the q-deformation. So the q-deform model was briefly presented in this reference here. It's also deeply related with Daha that was put forward by Cherednik more or less the same time. It seems that the two works were done independently. And then the model, well, the definition of the model looks very complicated and hard to make use of it. Uglov did a very deep analysis of the model, and then Jules simplified the formulation of the model. So he invented this representation that I will present here. So now, what happens? How does one deform the expression of the interaction that we have seen before? So the potential has to the potential is modified by this point splitting. So the 1 over sine square becomes this product of sinus, and then the spin interaction now will involve all the spins between I and j. So the basic ingredients here are the following. So there is an interaction which generalizes the antisymmetric projector, which was Pij minus 1. So this is now the Q antisymmetrizer, which is also the definition of a temporary leaf generator. And then there is the crossing of two lines is represented by this R-check matrix, which can also be defined in terms of the temporary leaves in this way, with a function with the explicit function f of u. So now with this graphical definition, the spin interaction will be this relatively complicated term that is represented here. And you see that it's not left-right symmetric. This is why I put a small index left here. In fact, there's another Hamiltonian, which is the other chirality, where you start with the spin at the position range. You transport it to the right, interact with the temporary leaf, and then go back. So the two, it happens that the two Hamiltonians commute with each other, so they can be diagonalized simultaneously. And there's another nice feature of the model. So if you take the same with the same representation, you can deform version, you can give a version of the translation operator, which is q-deformed. So translation operator in the isotropic case will be just product of permutations, which give a circular permutation on the lattice. So here this q translation operator is a little bit more complicated, but it still has the property of discrete translation operator, which means that if you do it n times, you will come back to the initial position. So now these three operators here commute, so it should be equal to 0. So you can diagonalize the three operators together, and you will have a basis of quasi-momenta, which are the eigenvalues of this operator. So although the model is not strictly periodic because of the fact that this interaction is not translation invariant, it still looks like a periodic model. And all the story that I had before about the extended symmetries gets extended here. So instead of having Yangian symmetry, we have quantum affine symmetry, where again we have the motifs, and the dispersion relations can be written in terms of one particle dispersion relation, which are a little bit more complicated. They contain q's. They are not real for q unimodular, but one can define a combination of left and right Hamiltonian that has a real spectrum for both q real and q unimodular. And the spectrum of this combined non-chiral Hamiltonian is just a Q-number generalization of the Haldane-Shastry spectrum. And of course, if you look a little bit at these energies, knowing that the Q numbers at Q equals I, the even Q numbers are 0, you see very quickly that there will be a lot of zeros in the spectrum, extra degeneracies in the spectrum of the Hamiltonian. So yeah, so it's looks like a curiosity. So okay, let's in order to give another formulation of this model, I will introduce non-unitary fermions. So as I was saying, Q equals I is like delta equals 0 for XXZ, so it's a model of free fermions. There will be some Jordan-Wigner fermions that I will denote with C and C dagger, which will come from the representation of the spin operators in terms of fermions. It's useful to introduce this staggering here, introduce some complex factors in the definition, redefine the Jordan-Wigner fermions with these factors. So you see that the anti-commutation relation will get plus minus 1 depending on the site, and these operators enter naturally in the definition of a global GL11 algebra. So for GL11, we have two fermionic operators, F and F dagger. They anti-commute to some central element, E, and there is a generalization of fermion number staggered, so that will be the number of C's, but here with the change of normalization, it will be staggered. And so you see that the representations will be labeled by the value of the central charge, which will be plus or minus 1. So you see the difference between even and odd number of sites, because for n even, the value of the central charge will be 0. So this will allow some pathologies to appear in the representation theory. Okay, so it's also useful, but not compulsory to use some two-site operators, fermionic operators that will render our formula a little bit simpler. So this with these two-site operators, one can represent the temporary Lieb generators at the free fermionic point. So they will be just G dagger G. The temporary Lieb algebra, well, I don't think I have to explain here what is temporary Lieb algebra. So the E square at the free fermion point, delta is equal to 0, E square will be equal to 0. So this is important for us. And as you probably also know, the temporary Lieb algebra is the commutant of UQ of SL2 for the XXZ spin chain. And when sending Q to value is equal to I, UQ of SL2 will become GL11 augmented with these two operators, which are quadratic in fermion number. So these are useful objects that will allow us to rewrite our Hamiltonians. So we started with two Hamiltonians left and right in terms of spins. So if we are doing this Jordan-Wigden transformation, we'll end up with Hamiltonians which are written in terms of in fact nested commutators of the temporary Lieb generators, which will be so if you take nested commutators of successive temporary Liebs, otherwise they will just give 0. Also, one can take in the expression of the Hamiltonians, we'll have also the individual temporary Lieb operators that I will represent by S commutator at equal sites. So in terms of this nested commutators, my Hamiltonians are, well, nested commutators times are some coefficients that can be computed explicitly. So they are some complicated combinations of tangents of this type, tangent of pi k over n, with k integers between 1 and n. So one can check that Hij for the right coefficient plus Hij for the left Hamiltonian are strictly equal to 0. So H left and H right, H left plus H right, the total Hamiltonian is 0. We can see that the associated energies are 0, but this is true at the operatorial level. So we have only one independent Hamiltonian here. But if we go further and we expand in powers of q minus I, we'll get a Hamiltonian which is non-chiral, so it's next order of Hamiltonian in expansion of q minus I, which is now given in terms of anti-commutator of nested commutators, and then some coefficients, complicated coefficients. And then we have our quasi-translation operator that can be also written in terms of temporary Liebs and these coefficients here. So now we have we express our spin Hamiltonian in terms of fermions. So if you look carefully here, this is in fact just quadratic in fermions, and this is at most quartic in fermions. Yes, so this is a kind of generalization of the XXZ Hamiltonian, open XXZ Hamiltonian with particular boundary conditions that preserves UQ of SL2. Because it's only expressed by temporary leaves for sites from 1 to n-1. So there is no term which will connect n to 1. So the model also has the Hamiltonians can be rescaled to have real spectrum in spite of being non-unitary. So probably this is due to the PT symmetry. There are other examples of PT symmetric Hamiltonian which have real spectrum, non-unitary, but they have real spectrum. So the parity which will flip the fermions on the first with the last fermion on the lattice. So it will exchange H left and H right, and it leaves the non-chiral Hamiltonian unchanged. There is also time reversal action and the charge conjugation. So these symmetries are acting on the conserved quantities. So now let's look at what happens with the spectrum and the spectrum at odd number of sites. The quasi-momentum is given in terms of numbers of motifs. The chiral Hamiltonian, so left or right, is given by this alternating values of the and linear and chiral version of the spectrum. So you see that if n is even or odd, you are on different branches of this dispersion relation. While the other the non-chiral Hamiltonian, it's symmetric with respect to n goes to n minus n. The value of the individual energy is just the modulus of the other energy, and they are perfectly linear. We can also find this dispersion relation. So first we had this dispersion relation directly from the expression at generic Q, but you can also get it from the fermionic representation by defining some new fermions using the quasi-translation. So you take the fermionic operator at the first site, and then you act with a power of quasi-translation operator, and you define a fermionic operator at a different site. And since g to the n is 1, this transformation is periodic. So the anti-commutation relations of this very similar to the canonical one, just they are non-local. So you see that phi a and phi dagger j relation for any sites I and j, but the result depends only on the distance between the two fermions. And so that was the expression on the in the coordinate space, let's say direct space. There is we can go to the Fourier modes, transform the Fourier modes, and also rescale a little bit the different modes of Fourier modes. And we scale them to get canonical commutation relations, which looks like this. So the zero modes, the modes with n is equal to 0, are nothing else than the generators of the GL1 algebra that we have seen before, the sum of f's and f daggers. And the others are some particular linear combinations of the fermionic operators. So in these variables, the chiral Hamiltonian become purely quadratic. So we'll get the dispersion relation here explicitly in the expression of the fermions. So you see that once you have a quadratic expression like this, this can be diagonalized into Fourier space, where you take all the possible action of psi's, provided that the n's are different, because you have fermionic statistics. But this is somehow looks contradictory with the fact that the spectrum was written in terms of integers, but which had the statistical repulsion. So they had to be different by at least 2 units. And in fact, because of the particular dispersion relation that we have, the two rules are compatible. So it's a bit surprising, but yeah, there is a compatibility between the motif rule and this fermionic occupation. So of course, it's not going to happen for any fermionic system. And now the non-chiral Hamiltonian, as I was telling you, it contains also a quartic term. There are some matrix elements which obey the selection rule that initial state, the energy of the initial state with respect to this Hamiltonian goes to is equal to the energy of the final state. And also the expression of the matrix element is given by this simple, well, it's rather, we notice it by numerical experiments. And so also this is what this expression is consistent with the rule that I mean the fact that eigenfunctions will be given by the motifs. So that's more or less the story for the for n odd. What happens for n even? So we have some preliminary results. What is the problem with n even? You see that if that n is even, then when k here is equal to n over 2, which is an integer number, then this object will become infinite. It's tangent of pi over 2. So some of the coefficients of my Hamiltonian will become infinite. So I have to regularize these coefficients. So I can regularize them by introducing a little bit of shift. I mean, shift these values, and then take the residue. I mean, take the limit of residue of the double pole of that quantities. So this will define me two other Hamiltonians, which will have finite coefficients here. which are again combinations of nested commutators of temporary leap generators. Sorry. The quasi-translation operator also diverges and has to be renormalized. So the expression of G plus and G minus. So one has to renormalize separately G and G minus 1. So we get two different versions of the regularized operators. So all these operators will commute, and they are nilpotent. So the spectrum of all the conserved quantities is 0, and the spectrum is given by a Jordan block up to size to the half of the size of the system. So this is a very strange situation. Also, if to understand a little bit how it happens for simplest example, smallest non-trivial example, at n equals 2. So before rescaling, the Hamiltonians they will be given essentially in terms of this single generator, temporary leap generator. And if you diagonalize this, you will see that you get 3 zero eigenvalues, which correspond to the q-symmetric states, which are given by these combinations of states for arbitrary q. And there is one q antisymmetric state like this with eigenvalue 1. And when you are sending q to I, you see that this coefficient here explodes, and these two vectors start to be aligned. So there is a sign of some pathology. So you see that before rescaling, although some matrix elements are infinite, the spectrum is finite and not identically 0. But after the rescaling, one has a finite Hamiltonian with four vanishing eigenvalues, and the eigenvectors form in the composable representation of GL11. So if you go at higher, bigger sizes, you will get a lot of in the composable representations, and the different representations will be connected together in a complicated manner that we still have to disentangle. And it's more than just a representation theory of GL11, because the Jordan blocks that we are seeing have a size more than 2.